This is St. Hildas Science Buzz, and here is your daily dose of physics. Please welcome today's physicist, Dr. Mussade.
Welcome and tune in, as today we'll be taking a closer look at the motion of vehicles in regards to velocity, acceleration and deceleration, as well as how the overall motion of vehicles can be plotted on graphs. A team of 3 physicists will be conducting an experiment to analyze the motion of a bicycle compared to a scooter over the distance of 20 meters on a road. Then we will change the surface to a grass track to understand the effect a rougher surface has on vehicle movement. To complete this experiment, a number of processes take place. The first step is the gathering of required materials, which include 21 colored cones, a phone camera capable of recording slow motion, a 20-meter measuring tape, a bicycle, a scooter, a smooth road surface, and a grass surface. Once the necessary equipment is collected, set the cones apart with 1-meter intervals in a straight line spanning 20 meters. Then, organize for someone to record each run with the scooter and the bike. For consistency, the front wheel will begin on the 0-meter mark, and the back wheel must finish on the 20-meter mark to complete the full distance. The bike or scooter rider should attempt to pedal or push as hard as they can to achieve maximum speed until they need to brake so the back wheel can stop on the last cone. Repeat these steps with the bicycle on the grass surface. The scooter begins to accelerate up till the 10-meter mark, then it continues at a constant velocity up till the 15.5-meter mark, and then the deceleration phase occurs up till the 20-meter mark. The first graph portrays the distance-time correlation of the scooter traveling on the road. The average accelerations in each section of motion is 0.29 meters per second, 0.11 meters per second, and negative 0.25 meters per second respectively. As shown in the velocity time graph, the maximum velocity reached was 0.7 meters per second. The bike on the road accelerates up till the 8-meter mark, then it continues at a constant velocity up till the 17-meter mark, where it decelerates till it stops at 20 meters. The second graph depicts the distance and time correlation of the bike traveling on the road. The average accelerations for each section of the graph are 0.11 meters per second, 0.08 meters per second, and negative 0.15 meters per second, respectively. As shown in the velocity time graph, the maximum velocity reached was 0.5 meters per second. The bike on the grass accelerates till the 9-meter mark, then it continues at a constant velocity up till the 16-meter mark, where it decelerates and comes to a halt at the 20-meter mark. The third graph is a rerun of the bike. However, we have kept the variable of the vehicle used constant and altered the surface. This experiment was run on a grass surface over the same distance of 20 meters. The average accelerations calculated for each section are 0.09 meters per second, 0.05 meters per second, and negative 0.13 meters per second, respectively. As shown in the velocity time graph, the maximum velocity reached was 0.4 meters per second. When comparing the scooter on-road results to the bike on-road results, the scooter has a higher average velocity of 5.7 meters per second than the bike's average velocity of 3.3 meters per second in all phases of the graph, and the scooter also accelerates for longer. A reason to support why the scooter can travel at a higher velocity over the same distance is because the bike is heavier, therefore it has greater inertia, making it more difficult to move. This relates to Newton's first law of motion. When comparing the results collected from the bike on the road surface versus the grass surface, we were able to conclude that the grass surface slowed the bike down, hence its relatively lower velocity and acceleration. Friction caused by the grass surface was a force that opposed the relative lateral motion of the bike's tires, making it more difficult to pedal. The uneven surface also made it difficult to balance the bicycle, hindering the streamlined motion of the rider. There were some constraints encountered in the undertaking of this experiment. Parallax error was the main constraint as a result of the video camera pivoting from a single point, which forces readings to be made from oblique angles, likely producing false results. The inaccurate timing matching between the video and the time at meter intervals is a potential contributor to minor discrepancies in results. In conclusion, the results collected from all experiments teach us that there are three key sections of acceleration, constant velocity, and deceleration. We were also able to link the causes of slower movement on the grass to friction and the scooter's higher velocity to less inertia. The results support the idea that a rougher surface slows you down due to an introduced variable of higher friction. However, the difference in velocity of 0.33 meters per second is not as significant as what would be expected. Time to put the brakes on. Dr. Mussade signing out.